is when I put them in the bag, perhaps you should check that I haven't switched. Okay, no, I didn't switch.
You just have to specify this.
Okay. Okay, so perhaps we get started. So yesterday we talked about scattering and solving the scattering equation, and even though you didn't have to write the code yourselves to solve the scattering equation, I did mention that the method that was being used was a finite difference method, so it was direct integration of this differential equation. It's a second order differential equation with certain boundary conditions, and you integrated through this direct integration routine, you integrated out, did the matching at large distances. Now today I want to talk about two different ways of solving the same problem, and they have their advantages, and we're going to revisit these methods at a later stage. So there's the way you're solving the problem at the moment is the one that's most suitable for the simple problem, but as problems get complicated, there may be situations in which the method you're using now is no longer valid or no longer the most efficient. So let's talk about other ways of solving that problem, and I want to touch on the R-matrix method. The R-matrix method is going to be back on the third week, but I want to introduce the concepts in the context of a single channel scattering. So you want to solve the problem, the Schrödinger equation, scattering Schrödinger equation that involves matching to infinity, but instead you're going to solve the problem in a box. So let's define a box with a certain radius A, and let's define a basis states inside this box that basically corresponds to the same equation that we had yesterday, but now I'm going to impose fixed logarithmic derivative at the border of the box. So this is the condition that I need to impose, and the reason why I need to impose it is because I want this basis Wn to be orthonormal. And you can prove that, so if you've worked out already all the homeworks, this is another nice analytic derivation that is proved that if you have a fixed logarithmic derivative at the border of the box, the set Wn is a complete set and can be made orthonormal. In other words, it is orthonormal. So Wn overlapping with Wm is delta and m. So if this forms then an orthonormal set, you can expand your solution in terms of these basis states. And that gives you the solution everywhere inside the box, which is where these states form an orthonormal set. Naturally, they do not form an orthonormal set outside the box. They're just nothing outside the box, but inside the box, they give you a complete set. Of course, just by applying the inverse of this, you can determine the expansion coefficients directly from that integral, as I defined here. So after some manipulation of, and I'm not going through everything, but now you've got you've got your conditions for chi of r and chi prime of r at the border of this box. You can derive this equation that relates chi of a and chi prime of a plus beta minus beta chi of a with a sum over Wn of a squared over the difference between energies. So what I didn't derive from here to there is necessary for you to understand the method. So I would advise you to go through that also. I didn't put it here as a homework, but I think I now realize that this is actually a larger step than I realized when I wrote this. So this is, it suggests it's not quite inverse logarithmic derivative the way we've defined it before, but it suggests a generalized logarithmic derivative. For beta equals 0, it is what we normally call the inverse logarithmic derivative. We can generalize that definition such that this becomes the new R matrix. And so if we have this generalization, then the single channel R matrix will just be given as a sum of the values of those eigenfunctions at the border squared divided by the difference between the eigenvalues that I get from solving the problem inside the box and the energy at which I want to calculate the scattering. If I have this, which means that once I've solved the problem inside the box and I get the set of WNs, then I can construct the R matrix, and from which I can extract an S matrix and construct the observables. So this is the idea of the method, and I just give an additional definition here that you'll probably use later. It's very common for people to introduce reduced width amplitudes associated with this renormalized value of the wave function at the border of the box, and then the R matrix is written very simply as square of reduced amplitudes divided by the difference between the energies. So how does it work? If you want to solve the problem in the box this way, so essentially it involves solving the single bound state equation. It's a sort of a bound state equation because it's inside a box. You don't have to go to infinity. You don't have to match to some Hankel combination of Hankel functions. So it's relatively simple to do for this case, but it's actually harder because for each value of L, you have to calculate a whole set of those WNs and then do the sum and construct the R matrix from the sum. So it certainly costs more for the single channel case than what it's worth. The direct integration is more efficient. I use it here just to introduce the concept and to show that you can, by solving the problem in a box, get information at the boundary of the box about the scattering, which is basically the concept behind the R matrix. Here is an example for the scattering, for one channel scattering of neutron on alpha at 5 MeV. So there's some effective interaction that is used between the neutron and the alpha particle, and depending on the number of N involved in this sum, so you're going to include a certain number of poles in your decomposition of the R matrix, and you're going to sum up to the point where you get convergence. In this particular example, the logarithmic derivative was chosen, beta was chosen as 0, which is not ideal for scattering calculations, so it could be optimized, but for this choice and for a box of the size of 8 Fermis, this is how it works. If you only choose 3 basis sets, you get a huge kink at the border. There's continuity of the function, but because you forced all the logarithmic derivatives to constant, you don't actually get continuity of the derivative. So you get these kinks that actually get removed as you increase your basis set. So what it shows here is that for a basis set of 20, you get pretty much a smooth curve. So I will see how we do. There's much more, as I made the comment here, there's much more on this in the 3rd week. And I will see if you can work out the method to this point, and if not, we can come back to that. Okay, next method. So actually trying to expand the wave function in some way inside the box is one way of solving a single channel scattering problem that is very useful in multi-channel and more complicated problems. The other way that I want to discuss is integral forms of solving the same problem. So I can transform this equation into an integral equation. And I'll do it very naively here, and then we'll actually work it out in coordinate space in some detail. So let's think of the Schrödinger equation, which at the moment we probably didn't. So Schrödinger equation, let's write it down like this. Or actually, it's convention to write it the other way around. So let me just keep it like that. And let's say my Hamiltonian contains some long-range interaction in addition to the kinetic energy, plus some other interaction. Okay? Let's say this long-range interaction I actually know how to treat. I can split it actually in any way, but let's say I know how to treat this part, and this is complicated. I don't know how to treat. So I actually know how to solve the problem like this. I know the solution, I know phi, but psi is harder because there's this other thing. Okay, so then I can write down this equation as an inhomogeneous equation. Okay, I write down the problem as an inhomogeneous equation, and I say, well, I know how to solve the homogeneous part. I don't know how to solve the rest. So what I'm going to do is the solution for an inhomogeneous equation is the homogeneous solution plus any particular inhomogeneous solution. So I can just formally write this. I'm going to introduce, I'll say, well, this is kind of a complicated operator. I'll call it G, and I'll call it GC. And then I get psi equals phi plus GC v psi. Now this turns out that for all purposes is actually an integral operator. And so we've transformed what used to be a differential equation, second order differential equation, into an integral equation that is implicit in psi. We haven't actually done anything because psi appears on the left and the right. But what I'd like to spend time today is discussing formalisms that are based in integral forms instead of the differential forms, because they open different perspectives in how to solve the problem that are going to be particularly useful when we don't know how to solve the problem. Okay. At the moment, I'm giving you the single scattering case. We know how to solve it. You solved it yesterday. You solved it through direct integration. It's easy. It takes milliseconds. It's no big deal. So I'm going to do it for an interaction like that, just as an illustration. Eventually, by the end of the day tomorrow, your hairs will be going up with so many different channels that you have to consider, and then you'll see that there's a purpose beyond the one that we're using today. Okay, so let's do, we have to do a little bit on green source. So what I did here is kind of formal, but really this object, I mean, what allows me to write this? And it could be ill-behaved or so on. So we want to see this in detail for coordinate space. So if you haven't seen it before, at least you go through it once and see that it is that function or that operator or that propagator or whatever I use to define that G can be well defined. And I'll do it in coordinate space. In momentum space it's easier. So you can do it in momentum space. And I'm going to start there, and then we'll go through some slides. let's go back explicitly to coordinate space. And I'm going to go through some of that, but now explicitly in coordinate space. I have E minus T minus VC that now depends on my coordinate. Chi L, I have a partial wave decomposition, so really to be accurate I should have T of L that has the centrifugal barrier, or perhaps I put the centrifugal barrier in the interaction. Well, it doesn't really matter. I might put it in there. And then I have something that's short range. And the interaction, so the condition is that this interaction should be short range. I can't have infinite range in that interaction. If you remember still, the boundary conditions when r goes to infinity for this chi can be written in terms of FL of r, and I'm dropping the eta. I'm going to drop lots of things as I go along, so please, please either remind me or then bear it in mind. So actually here I have Coulomb, so I have to put eta there. That's not, okay, I'm going to drop that eta. I don't want to carry that eta all over, okay. So we've got boundary conditions that I wrote in terms of a T matrix explicitly. Remember yesterday we also had the H minus minus SL H plus, and I said that you can rewrite this in terms of a T matrix. This is the time when I decide I want a T matrix. And it may become obvious in a little while why. Okay. I'm going to transform this equation explicitly by multiplying 2 nu over h bar squared. You remember that that's what comes in front of the second derivative, so that then I just have second derivative minus some renormalized v of L, chi L of r equals 2 nu over h bar squared v chi L of r. And now this v tilde CL is the Coulomb plus centrifugal. Okay. So have I dropped already something I shouldn't have dropped? I'm sure this will happen, or signs are different or anything. Let's define a source term, omega L of r, that is v chi L of r. Okay? I'm going to define my source, and the equation then is written just in terms of the source. Omega L of r, and any source can be written as a superposition of sources at various points in space. And this allows me now to introduce Green's function methods. So I'm going to take this decomposition of the source, and this means that my solution is also going to be, if I have the result for a delta function, then I can construct the final result as a superposition of those various contributions. So what I need really is the solution for this equation. I'm going to call the solution G plus. It has to depend on r and r prime. And then once I get the solution for this equation, my desired solution is going to be a superposition to nu over h bar squared integral G plus r r prime omega L r prime dr prime. So if I get a solution for this equation, which if you compare to here, it just means I'm looking at the delta source. then the solution can be constructed as a superposition. So it's going to have this term, which I know is the solution for the homogeneous equation. So remember what I said, the solution for an homogeneous equation has a solution for the homogeneous plus the inhomogeneous solution that will be constructed from the Green's function, which I now can call Green's function. So okay. Formally, what I have here is what I wrote here. I didn't do it in coordinate space, but it's the same thing, right? So here it's written formally. I took no care on what, how to invert these things, but it's the same thing. We're talking about the same thing. So now let's work out the solution. So let's solve the equation, essentially. So let's fix r prime, and let's consider r different than r prime. Well, for r different than r prime, then the delta is 0. And so the equation boils down to d2 dr2 vc tilde of r plus k squared g r prime equals 0. Well, we know the solution then has to be a combination of, well, two linearly independent solutions, and I can choose any two linearly independent solutions. So I could choose h minus and h plus. I could choose f or g, but I'm going to choose f and h plus, which is the way I'm going to want the asymptotics to look like. So I know my solution g of r prime has to be a combination of an f of r and an h of r. And now the coefficients in front, in principle, can depend on r prime, right? I've fixed r prime, but in principle these can depend on r prime, so I'm going to introduce some function of r prime as a multiplying factor in front of this linear combination. Now we want to determine these coefficients, and we're going to take the asymptotic conditions, the boundary conditions that we know physically this system has to obey. So let's consider r smaller than r prime, and for this case let's consider specifically r equals 0. For r equals 0, we know the function has to go to 0, has to be regular. So 0r has to be 0, and from here you can immediately see that this part has to be 0. So h of r prime needs to be a 0 valued function in these conditions for r smaller than r prime. For r larger than r prime, we can consider r going to infinity. When r goes to infinity, we know my asymptotic condition has to go as the Hankel function. It has to be, I want it to be actually an outgoing wave, so it has to go as h plus. So with these asymptotic conditions, then I obtain a condition for f of r prime being 0 for this to be satisfied. So now where are we? We've got a function f of r and r prime that has f of r prime f of r for r smaller than r prime, h of r prime h plus of r for r larger than r prime. That's how far we got. Now we use the differential equation, integrate the differential equation, impose continuity of the function. So if our differential equation, just writing it again, is this one I'm going to integrate this on both sides. And I'm going to integrate over dr from r prime minus to r prime plus. So I just want to integrate it over the delta function. So these terms do not contribute in the end because r prime minus is infinitesimally different from r prime, so it's approaching it. So these two contributions are 0. What survives are the contributions of the derivative at r going to r plus and r minus, and this integral, which is 1. So this implies, if you look at the expression that I obtained before, this implies that h of r, h plus prime of r, minus f of r, f prime of r, is equal to 1. Sorry, I don't think I can take this away. I will avoid writing here, and I will move over to the other side then. We're nearly there. So we also have continuity of the wave function. So this is the derivative from the integration, but also of the propagator. So h of r, h plus of r has to be equal to f of r, f of r. Because at r equals r prime, they have to be continuous. So now we just have to combine these two in order to get the solution. I prefer not to get rid of that. So once we combine those two, I mean, I worked it out. It's still a few, worked it out in detail, but I'm thinking, do I do it? Do I not do it? Why not? Okay, I'll do it. H of r can be extracted from the top as f of r over h plus of r. So from the continuity equation, you get this. Then you can get, plugging it in the other equation, you'll get this equation for f of r. This quantity is actually called the Wronskian, and it is well-valued function is minus k. So you plug that in, and you also plug that in, plug this definition up in there, and you end up with a Green's function that is minus 1 over k, h plus of r prime, f of r for r smaller than r prime, and f of r prime, h plus of r for r larger than r prime. And often it gets written as f for r minus, h for r plus. So if you see, f is always the value that's smaller between the r and r prime, and h is always the larger. Okay, so we know what the Green's function looks like. We know the solution for the delta function, so now we can construct the final solution as a superposition of these functions. So remember, chi of L is f of r plus, actually minus, now because of the minus that I dropped there, by the way, 2 nu over h bar squared k, so the k that comes in, and then you get an integral of FL of R minus H plus of R plus, larger, sorry, omega L of R prime dr prime. So note, we had asymptotic condition here. This asymptotic condition can be compared with the solution that I obtained here. And when you make that comparison, you conclude, well, the T matrix applied to H plus of L is equal to minus 2 nu over H bar squared K, H plus L of R, for large values of R, so R go to infinity. So I'm going to pull that out. The integral is over R prime. Sorry if, are you all with me? So this step here, that's going to be, R is going to be the large one because I'm looking asymptotically. Asymptotically, this term will look like this integral FL R minus, which is going to be R prime, V chi L of R prime dr prime. Yes? Well, if yes, I didn't hear the yes, but if yes, if there's nothing else missing there, then it's pretty clear that I'm getting a definition for my T matrix. The T matrix is actually just minus 2 nu over H bar squared K, integral FL of R prime, V chi L of R prime dr prime. So I explicitly derived an equation for the R matrix, for the T matrix. Typically this expression, if I write it in bracket notation, will look like this. Very important detail is the fact that's not conjugate. This thing here is not conjugate, and so that has incoming boundary conditions. Okay, this that I've written here is going to appear again and again later this week and next week. We're going to use the T matrix multiple times in this form, or in similar form. Any questions up to here? Oh my goodness. Oh my goodness, what are the units in the T matrix? I have to work this out. Has to be adimensional. So that's what needs to be worked out. So what we're going to do now is go through formal aspects. So this I thought was a useful exercise because when you just do the formal derivations, you don't really see how it applies in either coordinate space or momentum space. By looking at it in coordinate space, I think it's helpful because you can verify, first of all, that it's defined, that it is well-known functions, it's no mystery. And then this fact of non-locality, the fact that you have a dependence on the two variables that really justify the fact that you're pulling things from one place to the other. So it's that's the term propagator is often used in that context. So these Green's functions will now be used formally in just the way I've originally started by writing down things. But keep in mind that they have specific implementation when you project it onto either coordinate or momentum space. For those of you that have never seen Green's functions before, I think this is more useful than for those of you that have had full courses in Green's functions, because probably all of this was already done.
Why there is a minus between brackets?
Yes, that's a very important point that I tried to make. So there's no conjugate there, right? In everything I derived, I do not get a conjugate there. So when I write it in bracket notation, that has to have a conjugate, right? And the conjugate, if you think just in terms of e to the ikr, the conjugate of an outgoing e to the ikr is e to the minus ikr, so it's incoming. So the boundary conditions are different for that wave. Just in terms of plane waves, it will have a minus. It's coming in. That's why it appears there. It looks like an irrelevant detail, but it's actually very relevant. Many of us have been fooled before with that. Okay, so we did this. Basically what we did is we worked out what the equation should look like, what G should look like, and what the T matrix looks like in this formalism. And we're going to now look at formalism formally, just without worrying about implementation, and then we're going to derive very useful first of all, the two potential formula, so it's a very useful application of this formalism. And then we're also going to look at expansions that give rise to approximations, very useful approximations in this context. So what I just did, just summarizing, was to split the Hamiltonian between something that I may call a free Hamiltonian plus some residual interaction. In principle, I could just have put a kinetic energy term, or I could add the Coulomb. The condition is that whatever I leave out is short range. So it cannot be long range, otherwise it will change the asymptotic of that wave function. I have to know the homogeneous solution. So if I know the homogeneous solution, I'm done, because I can just solve this as an inhomogeneous problem, and the solution for the inhomogeneous problem has the solution for the homogeneous plus a specific solution for the inhomogeneous, where that G comes from the Green's function propagator with outgoing boundary conditions. So that's exactly what we solved. Writing it in short form, in formal way, I can write psi is equal to phi plus G plus V psi, which is an implicit equation. It is not the solution, it is another equation. But now it is an integral equation. So that Green's function operator is formally defined like this. What we did is actually work out this form in coordinate space. So I write side by side the integral versus the integral versus the differential equation. The integral form of this equation is referred to as the Lippmann-Schwing equation, and this one is referred to as the Schrödinger equation. So welcome to the two worlds, integral and differential. And physicists, theoretical physicists, divide themselves into those that live in this world and those that live in that world. And there's many of us try to bridge between the two worlds. But they actually are advantages and disadvantages in both methods. And so, whereas a differential equation, you have to add the boundary conditions. You add the boundary conditions explicitly. So in addition to these equations, you have two more lines usually. That is what the wave function needs to do at the origin and at large distances. Here you build it in the operator. So in cases where you really don't have an analytic form for your asymptotics, there may be advantages in building things this way. In cases like single channel scattering, I've already pointed out, it's actually more efficient to just do the integration. This form suggests, I pointed this out and I'm now going to milk this through. This form suggests specific things that you can do. An obvious thing is iteration. You've got a psi on the left and a psi on the right, so you can just replace the psi in there and iterate the equation. And that's basically what is done in this line. So where there is psi, I replace it again with that equation. And then you get the series. You get a series where you get the first term, that's the homogeneous solution, and then a propagator times the potential times the homogeneous solution, plus propagator, potential, homogeneous solution, etc., etc., etc. So you have a series that is referred to as the Born series, and that provides a picture for what is happening. Before I go to that picture, I want to rewrite this in T-matrix form. This Lippmann-Schwinger equation is written for the wave function. Few body physicists do not actually use this. They use a different form for this equation. If you define a transition matrix T that is actually the psi v phi, if the transition matrix is defined in this way, then we can use the Lippmann-Schwinger equation in the Born series, multiply on the left by this quantity here. So if I multiply on the left by that quantity there, then what I get is a T. And what you get in the first term is just the V in this plane wave representation, or in this phi representation. And if you look at what you obtain from this equation, then you get actually a T equals V plus VGT, which is the T matrix form for the Lippmann-Schwinger equation. So we're not going to use this, but I thought for some of you that might have overlap with few body world, this is what is typically used. So what we're going to use to a large extent is written here. So we've got a wave function that is phi plus g plus v psi, where again I insist phi is the solution for the homogeneous equation, and for the sake of this argument here, I'll consider it the free solution of H0, free solution, and then psi is the solution for the full thing. We already saw that the T matrix can be written in this form. This is literally this equation. And explicitly, it can be written as this integral. Now this here is not vector form, so if you want to construct the vector form for the T matrix, there's a few more steps needed. And I think that at least for now, I'm not going to go through those steps. I mean, I plan to go through those steps if I have time in the end. So the way to construct the full T matrix, one has to, there's no subscript cell here, but there's actually, should be subscript cell everywhere. You see, I actually wrote it on the board. I was less lazy on the board than I was in the slides. So this is for each partial wave. So for each partial wave, we'll have a T. If we want to construct the full T, we have to now sum over all partial waves and use the properties of the partial wave decomposition of spherical, of e to the IKR, right? So we can use those properties and construct this form that basically is saying the same thing. The scattering amplitude then relates directly to the T matrix, and so once you have this T matrix, you basically have a way to calculate directly your observables. Okay, so how am I doing with time? What's the time now? 20 to 12, okay. So two potential formula is probably one of the most useful things you might learn today. And I want to already say it is exact, okay? Some people at the end say, oh, but there's an approximation. It's exact. So let's start by setting the problem. a lot of ingredients here you have to keep in your mind because I don't have multiple projectors to keep it projecting. So you're going to have to retain some information here. Let's define a free wave function that I call phi. That is the solution to the free equation with no interaction. Associated with this, we will have a propagator, that is the free propagator, the Green's function. And I know that that free solution is actually just f of L. I've dropped the L coefficients, there's L's in all of this. Let's consider a distorted solution that includes an interaction, and it's an easy interaction. By this I mean it's something we can solve with our traditional direct integration methods. So the same sort of problems you solved yesterday. Let's call that U1, and chi is the solution of the equation. You will have, if you write it in integral form, so if I write this equation in integral form, then I can write it as chi is equal to phi plus g naught plus U1 chi, where g naught is the free propagator and U1 is that interaction. Okay, so I've got some distortion that I know how to deal with. Let's imagine that I have a full problem that I don't know how to solve, and the part that's hard is U2. I can do exactly what I did with U1, but now with U1 plus U2. Right? I can write a Lippenschwing equation that corresponds to a solution around this free solution. So if I pull these two terms over to the left or to the right, I get an inhomogeneous equation, and again I can solve it or implicitly in this way. So I get a solution that looks like phi plus an explicit solution, and the solution is going to introduce a free propagator because I'm putting in U1 and U2 on the right hand side. Of course, I could have done it differently, and then I'd get a different propagator. But for the sake of what I'm arguing now, I want this. Asymptotically, this chi goes as phi plus a Hankel function with a T matrix that corresponds to only action of U1. So I'm going to represent the T matrix by T1. The T1, what it means is that there's only the potential U1. In the second case, psi, I've got both U1 and U2, and so asymptotically it's got the same properties. It goes like phi plus some Hankel function outgoing, but with a T matrix now that has both potentials, U1 and U2. All with me? So do we agree on the definitions? So phi, chi, and psi. Good. Let's start. By definition, and it's nicely here on the board, I can write that T matrix, and I'm multiplying by that factor because I don't want to carry it around. I can write that T matrix just as an integral of the full solution, the solution that comes with inclusion of the full interaction, times the interaction, in this case it's U1 plus U2, times the free. So far, so good? Now I do a little bit of manipulation, and I replace that phi using this equation here. So if I come here and say, well, phi is actually chi minus this thing, I replace it. And now I decompose it. Well, then I'm going to get a term that is psi, both interactions, chi, and I get another term that has that operator, that propagator over there. So psi, full interaction, times chi, times some of the things. Okay, so I'm going to carry on rewriting that line that I just had. And now I'm going to use the second equation. Look at the second equation. The second equation has G naught U1 U2 psi. So I'm going to use that equation and replace it by psi minus phi. Are you all following? Okay, so now I notice that there's two things that cancel. So these cross terms cancel, and I end up with two terms. One that is psi U2 chi, another one that is chi U1 phi. Now that's kind of neat. I write it in bracket notation, and then I say, hey, these two things are actually T matrices but they're T matrices for different processes, right? This one is the T matrix that takes me through the operation of the second interaction U2, takes me to a distorted wave, and this one takes me from this distorted wave through the operation of U1 to the free. So this is kind of the effect of U2 on top of U1, and this is the effect of U1. So I'll write it down as the T matrix for 1 plus 2 is actually the T matrix for 1 plus the T matrix for the effect of 2 on 1. Now, if this does not ring a bell, it should, because yesterday we used this to compute Coulomb on top of, nuclear on top of Coulomb. Remember yesterday I argued that we should calculate the Coulomb separately because it's long range, and then we can add the nuclear on top of the Coulomb, and we'd have two terms. The scattering amplitude would be the Coulomb scattering amplitude plus the scattering amplitude of the nuclear on top of the Coulomb. That's exactly what was being used. It is exact. There's no approximation in any of this derivation. The slides are there if you need to work it out yourselves to believe in me, but this is a very useful expression because it allows you, if you know how to do something, you can do that part, and then you can deal with the complications on top of that part. Now this 2 on top of 1, what does it really mean in terms of the way I've defined it? It means this overlap between full wave function, U2, and the distorted wave function. So it still doesn't give you anything because you don't know that psi. So I'm afraid to say, even though we've played around with things, we still don't have a solution because it's still as a function of that psi, which is the solution of the full equation. So, you know, you haven't gotten away from solving the full equation. Not yet. But the point the important point is that this decomposition is exact. Even though it doesn't buy you all the way, it is an exact decomposition. So now the picture of the Born series. So I said, well, we have a Born series. If we iterate the equation, what we actually get is a first term that is the free term, and then we get propagates interaction times that free term, propagates interaction times free term, etc., etc. So it really is prone to this multiple scattering interpretation of what is going on. So you've got the no scattering case, the single scattering case, the double scattering case, and the triple scattering case, in which you've got an operator that is the interaction that is causing this transition, and then you've got between interactions a propagator that takes you from one to the other. So this is the picture to have in mind when you do this, the Born series. First term of the Born series, look what it is. What is it? Remember what the phi is? What is the phi? Sorry, I can't hear. The free, it's just plane wave, right? It's the free solution. It's e to the IKR. It's a plane wave. So does that ring a bell? I mean, have you seen that somewhere else? You've got e to the IKR, interaction e to the IKR. Have you seen this before?
It's first Born approximation.
Yes, it is a Born approximation.
Yeah,
But it's the first term. So that first term, you might have seen it before in this way. If you haven't done Born series before, I mean, if you've done Born series, then you know everything I'm saying. But if you haven't done this before, then you might have seen it in a different context and then not connected the dots. So this Fourier transform of the interaction that is usually used in an electron scattering comes from that first term of the Born series. So it is actually not very useful in nuclear physics. So I'm afraid to say plane waves, distortion is something that is very strong. This U1 that I was talking about is not a weak interaction in nuclear physics. it is a strong interaction, and therefore doing plane wave Born approximation, which is what this is called, is not a good approximation in general. Okay? So what we do is distorted wave Born approximation, where we already include some distortion in those plane waves. So let's do distorted wave Born approximation then. So then what we look at is the second term. So remember that we have the t1 plus 2 being equal to the t of 1 plus the t of 2 on top of 1. And the 2 on top of 1 is written in this way. So several things in the slide, so let's go by parts. I can iterate on psi and construct again a series, which now is a series that has the distortion in it. The first term of that series involves u2 as the interaction and the distorted wave chi. If I know how to calculate a distorted wave, which at this point you all do because you did it yesterday, then one could compute this first term just from that. Second term would involve a propagator G1 that now includes the interaction U1. So note that it's not G0 anymore. It includes, so the propagator includes the effects of U1. The other point I'm making here is terminology. We will refer to this as a post form. You could do a prior form where psi would appear on the left-hand side. So these things have to have symmetry, so you can write exactly what I derived. You could write it in terms of bras and eventually get something of this form. And so you can now do, again, an expansion, putting in psi, the Lippmann-Schwinger equation, and you get multiple terms, with the first one being of this form, chi minus u2 chi. So if you write down t1 plus 2, to first order, this post form and the prior form are actually equivalent. So what I have here is often referred to as distorted wave Born approximation, first order, or DWBA. And this is basically what I rewrite here. You can truncate the series to first order. You can truncate it to second order, and then you'd have to calculate this term, which is considerably more work than calculating this term, but can be calculated. So this propagator G1 will look a little bit like our propagator here that we derived, but it needs to, instead of just including the Coulomb interaction, it needs to also include the nuclear interaction, U1, if there's a nuclear interaction in U1, if U1 contains a nuclear interaction, which I think in general it should, because it's strong. So you can think of this as just a means of doing approximations if your difficult part, U2, is small, is weak compared to the rest. Okay, so how can you picture this? Let's say that you have excitations of a nucleus, and that's what you're trying to represent. So first order, it just means you can excite. Second order, it means you probably have, you either excite and de-excite, or you excite in 2 steps. All orders would normally be represented by arrows in both directions, which means you've included all the terms. What Antonio will talk about tomorrow will be starting from the all-order approach, solving the full coupled problem, and then doing truncations, so opposite direction. So just to recap, different methods of solving the problem. So we talked about direct integration methods yesterday. We didn't work out any of them. You were given a code that does it, but please look up, if you're interested in learning about the numerical methods, The one that you've been using is the Numerov method. Many of the scattering codes also use Ronch-Coulter method. So either one or the other, you have ways of doing the integration of that second order differential equation. You could do iterative methods on the differential equation. We didn't actually discuss them, but this is a standard method of also solving differential equations, not very effective for the sort of problems we have. I briefly discussed the R-matrix methods. You're going to get a lot more of that on the third week in a lot more complex situations. And rather similar would be to expand in pseudostates. So even though this is a scattering problem, you can try to describe the scattering problem as a superposition of things that look like bound states. And so this is a whole different class of things that I didn't get into, and that I mean, some of the people here have actually used them, so know a lot about it. The other class are the integral equations, and in the integral equations, the first and most naive way of solving these integral equations is through iteration. Turns out that not always the most effective way of solving the problem, because it's very sensitive to your starting point. You can also transform those equations into matrix equations and solve it that way, or you can do what I just described as a multiple scattering series that allows you to truncate up to a certain order, hopefully, if what you've left out is weak. One more comment, and we'll see how we're doing with time. I think there'll be a little bit more on that tomorrow. But I want to connect to what I said about the P and the Q space. And I think now with the Green's function methods more, with the familiarity with the Green's function methods, it's easier. So let's take the equation we had yesterday, a single channel equation, T1 plus U1 minus C1 psi. Now let's say that something else is happening. I know that the system, that target actually excites. So there's something else that's happening in my system. I'm going to call it a U2 in terms of interaction, and the channel will be a psi2. So there'll be some feedback of that additional physics into my channel. Let's call it V of U2 psi2. And then, of course, I can have also the equation for the second channel. So one can write the problem as a couple channel problem. And if you formally solve this using the techniques that we saw today, then you can literally work out from the second equation what psi2 needs to be, replace it up there, and get to this equation. So that if you replace psi2, so this moves over to the right, and you replace psi2 in there, you end up with a term in the interaction that is V12 G2 V21. So look at what happened. Your equation now looks like an optical model equation with a modified interaction. So it's very similar to what we discussed in terms of P and Q space. In this case, the Q space is the second channel, and the P space is the first channel. So you can see it very explicitly here, and just terminology. This U1 is usually referred in this context as a bare interaction, as opposed to the full thing that contains the effects of the additional channels on that channel. When you do an optical model fit, you fit the full thing. You don't actually see the details of what's bare and what's not bare. But as you start including more ingredients in your model, you will have to distinguish between what is bare and what is additional effects, what are additional dynamic polarization effects, or etc. Okay? Any questions? Are you ready for lunch, or should I derive some more things?
In this case, the definition of the G2 is the inverse of the T2 plus U2 plus U2 minus U2. In this case, you didn't show
No, I didn't, but it's just directly from the inverse of that second equation.
No.
Yeah, I didn't define it in this slide. I should have. So it's directly from the inverse. It's that term. Any other remaining question? Okay, someone give me the time. 12. And we only stop at 12:30, right? Okay, so I have time for more. I'm sorry. I saw some of your faces. Okay, let's look at this point because I brushed over it, and I think for some of you it may be, I didn't know if I was going to have time, so I'm going to go back. Where did I put that? Oh, no, it's not here. Ah, there it is. So I just said, yeah, we can go from here to there, right? And I didn't really say very much. Same with the R matrix. So I can go back to the R matrix derivation as well. So some of the things I skip because I'm not sure I'm going to have time to go through it, but you should go through it if I end up not. But this one is something perhaps we can do here in a couple of boards. So let's try and work out the relationship for the T matrix once we add up all the partial waves. So it's already explicitly done. So first of all, can you actually see the board okay? Everyone can see the board okay? Okay, that's good. We have to thank Marek for the nice pens. Okay, so let's consider, first of all, let's make it simple and let's consider no interaction, no Coulomb interaction, so that the solutions, free solution is VL of 0 R, and the full wave function is just KL of R through the interaction of a certain potential V. Okay, short range. And we're talking about elastic scattering. Let's make Ki equals K. So the scattering amplitude, when you decompose it in partial waves, is a sum 4 pi over K, sum over L and M of Y L M. So you can always decompose the scattering amplitude in partial waves. And the way you'd bring it back in total form would be by summing all those, but taking into account the various spherical harmonics associated with it, right? So this is standard partial wave decomposition written in full form. I'm also giving an equation for the plane wave, partial wave decomposition of the plane wave. Yesterday, I believe we had a plane wave decomposition in terms of Legendre polynomials. I'm going to write down the one in terms of spherical harmonics that includes projection, so that it's independent of the direction, in any direction. So then you get FL0 KR, KR, Y LM R hat, Y LM of K. That's the standard expansion. The other thing we're going to need is the properties of spherical harmonics. And so if you end up with an integral over 4 pi dr hat ylm asterisk of r hat v of r y l prime m prime r hat, your solution is going to be the v of r delta ll prime delta mm prime for central interactions. It's confusing, this thing. So what I wrote here, 1, 2, and 3, are just properties. I'm not actually doing anything yet. Now let's look at our problem. What we want is to write the T matrix. So that T matrix was defined, I have it there, 2 nu over h bar squared k phi minus v psi. So let's put it in. F of theta would be, so I'm going to put it in this expression. For each L, I'm going to put it in here. And I'm going to get the 2 and the 4 pi, 8 pi nu over h bar squared k squared. Now I get the asterisk in the spherical harmonics. The v of r KL of r. So actually here I'm already putting in an f because of my assumption and a chi because of my assumption. Okay? I mean, it can be general. It's just a matter of definition. So I can bunch up a few terms. If I bunch up this term and this term, sorry, not this term, this term, oh, sorry, this in principle is vector, so I have to replace by the decomposition. Yeah. So this has an additional line here. Sorry, I missed my line. So if you do it in full space, you actually get this. Oh my goodness, you're not correcting me. So this was prime, right? Okay, now I'm talking. Okay, so I had to introduce the R dependence here. There is a bug, pretty big bug here. So what I did here was replace this by its vector form, which is defined over here. So I could introduce it here. And now I've got all the elements. So now what we need to identify are the various elements that make a plane wave and put those together and then put together the elements that make the full wave function. So let's see if I can do this in color to make it more obvious. We need this, we need this, and this. All these I can construct a plane wave using those three terms and doing that sum. The other three actually represent the vector form of the wave function. So if I was to expand the full wave function in the same way, then I'd get this in vector form. So when you do the sum, I think it becomes more obvious that you're going to get rid of those three terms as an e to the I kr, and now you have to think about whether it's going to be minus or plus, and it depends on how many e to the I L factors you get. So what I write up here is a continuation where I've put together these terms and have the vector form of the potential of the wave function in them. And I believe that's literally what we want as the T matrix of k, ki. So actually I realize there's sums missing, right? So I didn't write the sums here. When you put in, the scattering amplitude will be a sum over all Lm. You have to put in the sums there, okay? I mean, I'm hoping that in your notes you're doing this with the sums. I missed out on the sums here. So if you collect the sums, you get a sum that looks like e to the ikr. Collect those that refer to this part, you'll get the vector form for psi, and you can write then the vector form for the T matrix defined in this way, and then the scattering amplitude relates to that directly, just like is over there. Okay, I think now I should be done.